Okay, the next couple of videos are going to be how we can alter the properties of a solution based on how many things we get dissolved in. And I say things because I mean it really comes down to how many particles are there. So the first thing I want to talk to you about is something called the Van Hoff factor, and it's represented in chemistry with the lowercase I. This is basically, it's a number that tells us how many particles will one molecule of some kind of solute break apart into. So let's look at a couple of examples and you'll see what I'm talking about. For example, sodium chloride. Okay, now sodium chloride, we know when we put that into water, this is an ionic compound, it has a metal and a nonmetal. This is going to break apart into a sodium ion that loses an electron and a chloride ion that gains one. But each single molecule produces two different ions. Okay, so we would say that the Van Hoff factor here is 2. Okay, it just tells us how many particles that one thing will break up into. If we look at barium nitrate, we know that barium will break up into an ion that's got a positive 2 charge. It loses 2 electrons. And then each of these nitrate groupings gains one of those. So I get a nitrate ion, and I get another nitrate ion. But there's actually 1, 2, 3 different particles that come from this original molecule right here. So my Van Hoff factor is going to be 3. Now, be careful. Just because it looks like there's a lot doesn't mean that there is. Okay, you have to recognize certain groupings. So for example, ammonium chloride, we should recognize that NH4 is one of those groupings that stays together. That's an ammonium ion, positive. And then we get a chloride ion, that's negative. So even though it looks like there's a lot of stuff here, it really only breaks apart into 2 different ions. So my Van Hoff factor is 2 again. Okay, so it's the total amount that they break apart into. These are known as electrolyte solutes because they'll make electrolyte solutions, which means you get these charged particles, these ions broken apart. Now, contrast that with sugar. Sugar is a gigantic hydrocarbon, really long molecule, but these are all covalently bonded. They're sharing electrons. When you put this into water, these sugar molecules will break apart from each other. So one of these molecules will break apart from another identical molecule, but the actual molecule itself does not break down at all. It stays together as C12H22O11 when it's made of all nonmetals, and there's no ion groups you would recognize like ammonium or nitrate. Then you recognize that we call this non-electrolyte solution. It's not going to break up into charged particles. These things stay together, and the Van Hoff factor here is 1. Okay. Now, in your homework, we're going to take a look at some electrolyte solutions because I want you having to interpret how many different particles they'll break apart into. Okay? Now, the other thing we got to look at, and this is going to sound familiar, but it's also going to sound a little weird. We're going to look at another way to measure concentration. It's been a while since you've done this, but you're used to dealing with molarity. There's another way of measuring concentration called molality. Sounds a little strange, but it's a slightly different twist on how we measure things. It's still moles of solute, but it's divided by kilograms of solvent. Okay, so not the overall volume of the solution, but the weight of the solvent we're putting it into. Now, for the purposes of this upcoming assignment, we're just going to stick with water as being the one we use, even though we could use alcohol or any other thing. We're going to stick with water right now as the one we're going to analyze. So for example, let's take a look at this, and then we're going to use the results from this, and I'm going to show you how we change freezing points and boiling points based on putting 45 grams of salt into 600 milliliters of water. So first, let's calculate the molality. We're going to take the solute right here, and we need to turn it into moles. This is pretty normal for us. 45 grams sodium chloride. I want to turn it to moles. So I need grams on the bottom, and then I get the molar mass from the periodic table. 23, 35.5. This is 58.5 grams per mole. When I divide those, I get a value of about 0.77 moles. Okay, now that's not the molality, but it is the moles. Okay, the next thing I have to look at is the solvent, the water that we're putting it into in this case. I have 600 milliliters of it. But there's some things you should remember about this. Okay, so 600 milliliters of water is also 600 grams of water because water has a density of 1 gram per milliliter. It's about the only one you have to memorize. Okay, and if that's 600 grams, it's also 0.6 kilograms. Okay, so that's the units that I'm going to need. I'm going to divide this by 0.6 kilograms. And when I finally calculate that out, I get a value of 1.28 and it's a 1.28 molal solution. That sounds weird. Okay, so the abbreviation here in chemistry is 1.28 with a lowercase m, and that represents molality instead of molarity. Now let's remember that number. We're going to take this solution, 45 grams of salt and 600 milliliters of water, and we're going to see what that does to its freezing and boiling points just based on this concentration and a Van Hoff factor. Remember, the Van Hoff factor here is going to be 2 because sodium chloride breaks up into 2 different particles, a sodium ion and a chloride ion. So we're going to take those 2 pieces of info, and in the next video I'm going to show you how to put those together into a simple calculation to see what happens to the freezing point and the boiling point.